Hello everyone. In this presentation, we will discuss how the control of the wind turbine system can be improved using nonlinear backstepping approach. So, our work entitled Nonlinear Backstepping Control of PMSG-Based Wind Energy Conversion System connected to the grid. In order to present this work in a more properly and organized way, we propose the following outline. First, introduction, population growth and the expansion of global developments in many areas have led to high consumption of electrical energy and also to high levels of pollution. Faced with this energy bulimia, countries around the world have turned intensively to clean renewable energies. As a developing country, Morocco is also experiencing an increase in demand and consumption of electrical energy. The Ministry of Energy Transition estimates that demand could reach 133 terawatt-hour by 2030, and thus consumption could grow by an average of 7% compared with the annual average. To face up to this situation and reduce the rate of energy dependency, the Moroccan government has engaged an integrated energy program which aims to increase the installed capacity of renewable energies to 52% in 2030, of which 20% comes from wind power. As a result, research and investments in wind power have increased dramatically. However, there are several problems associated with their integration into power grids. First, wind generation is intermittent and fluctuating in nature. Second, wind turbines inject harmonics into power grids. Wind turbines have an impact on power grid stability and the need of manage the power exchanged between wind farms and the grid manager. Before we start elaborating the control strategy, we will briefly introduce the PMSG-based wind turbine system model. In this slide, we have adopted the structure of wind turbines based on the permanent magnet synchronous machine because of the following advantages. First, operates over a wide speed range. PMSG with a large number of poles has no multiplier. Independent, easy control of active and reactive power exchanged with the grid. The parameters of the study are given by these two tables. Our system is composed of many components, but it could be simplified by using the following equations that describes the wind turbine, PMSG, and the filter model. We'll now turn to our conservation improving system control. As we know, the PA controllers are highly sensitive to different perturbations, resulting in degradation of system performance, such as sensitive to variation parameters, unsuitable for nonlinear systems, sensitive to uncertainty, modeling errors, and sensitive to external perturbations. To overcome these problems and improve the robustness, stability, and efficiency of the system, we have adopted robust disturbance and sensitive controllers based on backstepping controllers. The backstepping controller is widely used in the literature due to its advantages. The concept of backstepping control consists in decomposing the complex system into several subsystems. In each step, the virtual control of the subsystem is calculated to be used as a reference for the next subsystem until the control layer of the complete system is formed. Global stability is determined by the Lyapunov function. The control laws of the wind turbine system, specifically the equations for controlling machine speed, stator currents, and filter currents, are given by the following equations. To ensure system stability, we use the Lyapunov function given by these equations. Keep in mind that constant parameters must be chosen as positive. This figure illustrates the structure of the control system. Machine-side controller is used to extract maximum power from the wind, control the power, torque, and speed of the generator, control the KS generated by PMSG. In addition, the role of grid-side controller is used to keep the DC bus voltage constant, control the key exchanged with the grid, and the grid synchronization. Model simulation and the results. In order to validate the performance of the proposed controllers, simulations were carried out for 1.5 megawatts PMSG-based wind turbine system connected to the grid. A wind profile with a variable speed between 7.85 and 11.5 meters per second and an average value of 9.67 meters per second is applied to the turbine blades as described in Figure 1. The turbine speed and electromagnetic torque are shown in Figure 2 and Figure 3. According to this figure, the backstepping controller is able to follow the references with higher precision compared to a PE controller. This means that the backstepping controller extracts more power. The quadrature stator current Figure 4 is proportional to the electromagnetic torque. Figure 5 illustrates how the direct current oscillates around zero and is utilized for controlling the stator reactive power. Figure 6 illustrates the consistent maintenance of the DC voltage, remaining nearly constant and matching the desired reference value. The direct and the quadrature grid current components track their references as illustrated in Figure 7 and Figure 8. These figures show that the backstepping control strategy offers better tracking and high dynamic and steady state performance. Conclusion. A comparative analysis between the proposed backstepping controllers and conventional PA controllers for PMSG-based wind power system has been carried out. Despite their simplicity, conventional PA controllers are more sensitive to disturbances and less efficient to extract maximum power. Backstepping controllers based on the Lyapunov approach showed significant improvements in terms of maximum power tracking, dynamic and static response, as well as robustness. In conclusion, the backstepping approach proves to be a very attractive control method compared to PA controllers, as demonstrated by the simulation results. Thank you for your attention.